Hello.
Hello, YouTube.
Hello, YouTube. Okay, so what are we doing today? Surface area. All right. This is the last topic for this unit.
Oh, no.
Okay, so we've got, let's see, what do we got? Today's what, Tuesday? I think we're gonna go over some homework stuff tomorrow. And then Thursday's the pre-test and Friday's the test, right? So that is what we have. Okay, good. So, surface area today and tomorrow. Thursday's the pre-test, Friday's the test. And you got your results already on the portal for yesterday, right? Well, but it doesn't work. Yeah, that's okay. Kindly consider the following. What if I gave you the function y equals e to the negative x? Can you find the arc length of that curve from x equals 0 to forever? Yeah, I want the arc length. Is it? That's a good question. Is it forever? Sometimes the arc length, when you think it should be infinite, it really isn't. Interesting. Alrighty. So let's set up the arc length L. How do you do arc length again?
L equals
1 plus the derivative squared, square root it, then integrate from x equals a to x equals b dx, right?
Yep.
Okay. All right, who just came in? We got Cheyenne, we got Stephanie.
Mr. Garcia, your Wi-Fi's down.
My Wi-Fi's down? Huh?
The room.
Wi-Fi?
Yeah, I mean the internet's not
Oh,
working.
okay. That's fine. All right, you don't need it right now. Okay, so if y is e to the negative x, what's dy dx? Negative e to the negative x? Okay. And so what's dy dx squared? E to the negative 2x, right, okay. Okay, so how are we going to write this? The integral from what to what? X is 0 to... What I really want to know is, does it hit the x-axis? So keep on going until it hits the x-axis. In other words, keep on going forever. So I'm going to go from 0 to infinity. This is right, exactly. Square root of 1 plus that. Now, is there another way of writing e to the negative x squared? 1 over e to the 2x. I'm going to write it that way. Okay. Now, can you find that integral with like a u sub? Can you do an antiderivative here? No. All right, so we can do this. We can only do this numerically. By the way, this is known as an improper integral. If a is not a number, b is not a number, or somewhere in between the function's undefined, we deal with that in a special way, and that's called an improper integral. The way to do this is to take the limit as b gets huge, the integral from 0 to b. I don't know if you remember, we did something like that on the last test when we were trying to get the area under e to the negative 2.
Yeah.
Was that what it was? I forget what it was.
E to the negative x.
Well, yeah, we were just doing this part, right? E to the negative 2, right? And that was like a bell curve, and we're trying to get the area under the bell curve, and it said do it from negative 10 to 10, from negative 1 to 1, from negative 10 to 10, from negative 100 to 100, and we're trying to get to infinity. That's what we're going to do here.
Oh, that's interesting.
So let's do a convergence table. Exactly, right. Aha! All right, so let's do a little convergence table. Let b get bigger and bigger and bigger. Say 1, 10, 100. And evaluate this integral from 0 to b. Okay. So, what do you do? Get the calculator. All right, let's get the calculator out. So, This would have to require a calculator. Yeah. All right, so let's do a new document. Let's do a calculator. Let's do menu, calculus, integral from 0. And again, this is where it always gets stuck, right? What if I just hit enter? Did it jump? Here's x. Enter. Can I move it now? Come on. No. Okay, get out of here. It always does this. This is crazy. Okay. All right, so it's... all right, let's do from 0 to 1 of the square root of 1 plus 1 over... How about we make it rational? Control divide. 1 over e to the 2x. And you need a decimal where? Why? Well, let's see what it does. Yeah, apparently there is a way to do this antiderivative. We just don't know how to do it yet. So let's get a control enter would do it too, right? Yeah, we'll get to stuff like that eventually. All right, so there's my first result. Now I'm trying to get a convergence, right? On the AP, they like to get your answers to 3 places. So that's why I have this at fix 4, usually. I'll do a convergence table to fix 4. The 4th place, even if it converges, maybe having a little round-up error, I'm not going to trust it. Just take the first 3, right? So on my table, I'm going to write 1.1927. 1.1927. All right. Now what do you do? Do it for 100. Okay. Oh, for 10. Yeah. All right. So let's see. Let's capture this and redo it for 10. Go up. And you could do what? You wanted a decimal here?
Yeah.
You could do that or control enter. And 10.226. All right, so write that down. 10.226. Oh, I think it was, actually. Remember, it's in fix 4. Even if it didn't write the 0, there's a 0 there. All right, let's do it for 100. Alrighty. So, let's capture this again. Whoops, not this. This. There it is. And change that to 100. I should have probably made that a variable A or something. Just change A. Make it quicker. And control enter. And it's 100.2260. It's in fix 4, so there's an O there. Okay. So you tell me, is this getting closer and closer to a value, or is it getting farther and farther? Are the answers getting farther and farther apart?
It's diverging.
So is this a convergence table or a divergence table? So you're going to say that this limit? D and E. Okay. There you go. But sometimes improper integrals do exist. That's counterintuitive, but it's true. Now, let's see. How about this? What about the surface area? What if I take this arc and revolve it around the x-axis? This is a famous problem, by the way. This is called Gabriel's horn. Who is Gabriel? The Archangel Gabriel. Right? He has a big ass horn to call all the angels in creation in case there's an emergency. This isn't supernatural. This is for real. Okay, anyway, if you believe in such things, Christianity. All right, anyway. So Gabriel's horn. Now, Gabriel's horn is constructed such that it has this shape. It's infinitely long. It's really hard to drag around, but he's an archangel. It's okay. But now the question is, though, can you build it? What's the surface area? How much brass do you need to make this horn? The outer surface. I'm not talking about a volume. I'm not talking about an area. I'm talking about a surface area. Right? So if I take this and I revolve it around the x-axis. Revolve it around the x-axis. Alrighty. He's not here. Was that funny? Okay, Blake, you got mail. Blake. And Savannah, you get mail. I'm going to go postal in a minute. Huh? All right. So I got this big, huge horn, and at the end of it, you got Gabriel's mouth, okay? So this is where the sound comes out, right? Okay. Can you calculate the surface area?
Wait, do we have a radius of Gabriel's mouth to figure out to what?
Well, it's going off to infinity.
Oh, okay.
So, how do you get this area? Now think, sort of like shells, where we use the circumference of rotation. Can we do something like that? Yeah. Right. Let's take this, let's say a very thin piece, very thin dx, right? Piece of this horn, right? It's got a circumference times a piece of the arc length. Isn't that an area right there, two-dimensional? Yeah. Right there? Yeah. Okay, so that's what we're going to do. We're going to take our arc length and multiply it by the circumference of rotation. But the circumference of rotation, it varies with x, doesn't it? If you're over here, it's really big. If it's over here, it's really small. So how are you going to write the circumference? 2 pi r, but what's r? No. R is this distance right here. Which is who? It's e to the negative x. It's the y value there. It's a function value there, right? Okay, so I'm going to write this. I'm going to say the surface area of Gabriel's horn is 2 pi the integral from 0 to infinity of e to the negative x dl. Huh? What did I just do? Well, dl is what you're integrating to get the arc length. It's that. Right. So if you can set up an arc length, you can easily set up a surface area. You just multiply by 2 pi r. Okay. So what was it? Rad 1 plus 1 over e to the x squared? Okay. So let's write that. Okay. Is that a use up?
Wait, I thought that was Wait, you forgot to multiply by...
this is what we integrate to get L. That's what I'm calling DL.
Then you forgot e to the negative x.
There it is.
Yeah. Oh, I thought you were...
Right, 2 pi r DL. Right?
Yeah.
Sometimes these are easy to do. The antiderivative can be done algebraically. If you distribute what's here into there, or this is a use sub. I'm thinking it might actually be a use sub, but just for fun, let's do the convergence table thing again. Because what's the problem here? It's going to infinity, right? So I really can't do that. I'm going to say 2 pi times the limit as b goes to infinity of the integral from 0 to b of e to the negative x rad 1 plus 1 over e to the 2x dx. So let's evaluate that numerically. And so here's b. Here, let's do 2 pi times the integral from 0 to b of all of this stuff. That's an x, okay. And let's say we do it from, I don't know, from 1, from 10, from to 100, whatever, and see if this converges. Now, what's your intuition? The arc length did not converge. Do you think the surface area will converge?
Yeah.
That's what's weird about these problems. I think it does. All right, let's find out. Right, so let's go to the calculator. I'm basically doing this with a 2 pi e to the negative x in front, right? So I'm going to copy this. Or not. Ugh, wake up. Okay, I'm going to copy this. Let's go from 0 to 1. So I got to change this to a 1. But I also have to add to this an e to the negative x in front, right? So e to the negative x. Where's my negative? There it is. And a 2 pi in front. And you can put that in the integral or outside. Doesn't really matter. Well, let me get outside. Okay, 2 pi. There you go. All right, so that's from 0 to 1. That's the surface area from 0 to 1. And you get 4.88. Wait, hang on. Oh, yeah, that's right, yeah. 4.8. Oh, it's not in fixed 4, is it? Oh, well. 48492, let me write. 48492. 8492. Okay, now let's do it for 10. Did you get 10 yet? All right, so keep track on your table. What's going on? So let me copy this and make this a 10. There's got to be an easier way to change this. Can I just go? Yeah. 10. And Control Enter to get a decimal. And now it's 72115. 72115. 7.2115. All right, it's not growing really fast, right? Yeah. So it may not be blowing up. I don't know yet. Let's see if it's getting closer and closer to something. Still, let's try it again. All right, so let's capture this. And can I just go up? No. Over and up. What's the quickest way to the 10? Over, up. There you go. All right. 0 and then Control Enter. Oh, I hit Control twice. Whoops. And it's 72118. So is this converging? 7.2118. Well, I'm not done. If I want 4-place convergence, right? I'm not done. So 1,000? Okay. So is it the same? Yeah. All right. Let's just confirm that for everybody. All right. So just capture this thing again. Let's go a little bit in there, and then go up and make it a no. Dang it. Go into some more. Go up. There it is. 1,000. Control Enter. And 7.2118. There you go.
It's not a lot of brass.
No. Okay, so this one converged. 7.2118. All right. So I'm going to say that the surface area is about. Now I'm not sure if I'm fixed 4 or not. If I'm in fixed 4, there's Rundle error here. So I'm just going to say 7.211. That much I know for sure. Okay.
Yeah.
Any questions about that? All right. So Gabriel's horn is infinitely long, but you can build it. That's how much brass you need. If these right, because it gets so small, really it gets negligible after a while. So if these units, if X is in feet, we're talking about only about 7.2 square feet of brass. That's all you need, right? That's weird. That's really weird. All right, what if we change Gabriel's horn? What if we say this? The arc length is like this from X equals 1 on. And the curve is y equals 1 over x squared. Alrighty. So, you get the arc length. Go. I want the arc length from 1 to infinity in x. This is the different function. Can you get the arc length from 1 to infinity if that's the curve? That's what you come up with. This doesn't hit the y-axis. I'm going to start at 0.
Do you want the formula or the convergence?
Just set it up. What I really want to know is what's the surface area. So first set up the arc length. How do you set it up? Alrighty. You think you got it?
I think I do.
You think you got it? Let's see if this surface area converges. Alright, looking good. Well, then use that to set up the surface area, and then see if it converges. So y is x to the negative 2, dy dx, what'd you get?
-2 over x3.
Negative 2, x to the negative 3, right? which is negative 2 over x cubed. Okay, fine. And so square it, 4 over x to the 6th. All right, you need to do that somewhere. That's set up the arc length. You're trying to get the DL, right? All right, so tell me, what should I write? The integral from 1 to infinity of 1 plus 4 over x to the 6th in a square root dx. Okay, did you write s? All right, how do you change it? It's almost the same, really. 2 pi, the integral from 1 to infinity of x squared? 1 over x squared, is it?
Oh, yeah.
Yeah, 1 over x squared, or x to the negative 2, if you like, times the DL. All right, this is what I want to do. Can you do that as a use of? Oh, no, wait, I take that back. Wait. I take that back. I eventually want to evaluate all of these, but what I want to get to is, what's the volume of the horn? Sorry. What's the volume of the horn? How would you set up the volume? The volume is, let's see, we take vertical strips, and around the x-axis, is that going to be a disc washer shell? There's no hole in the middle. It touches the axis of rotation, so it's a disc, right? So you write pi, what? The integral from 1 to infinity of r squared. Now, what's r squared? 1 over x to the 4th. Or you want to write it that way? X to the negative 4 dx, right? Okay. Evaluate that first. Then we'll go backwards. We'll evaluate everything. Evaluate that first. What do you get? Does that exist? Remember, what you got to do is make it a limit as b goes to infinity, the integral from 1 to b, so plug in 1, plug in b, b's a number, pretend, right? X to the negative 4 dx. See what you get. And you can do that one algebraically. You don't need a convergence table, do you? This one you don't need a convergence table. What's the antiderivative of x to the negative 4?
X to negative 3 times negative 3. I mean, 3.
Right? So what do you get? You get pi, the limit, as b goes to infinity, of x to the negative 3 over negative 3, evaluated from 1 to b. Okay. So how do you do that? What do you do next? You plug in b, right? Now, this is really a fraction where the x's go where? On the bottom. So I'm gonna do it this way. Pi, the limit, as b goes to infinity, of, is it negative 1 over 3 x cubed? That's easier to evaluate the limits after you plug in the b's, right? So here we go. It's going to be, let's go over here. It's going to be pi times the limit as b goes to infinity of plug in b, negative 1 over 3b cubed, minus plug in a. But if you subtract the negative, you're adding, and if you plug in a is 1, and so this limit, you can do this in your head, can't you? It's 1/3 times the pi, right? This is bottom heavy. As b goes to infinity, this goes to 0, bottom heavy, right? Okay, so 0 plus 1/3 is 1/3. That's the limit times the pi. It's pi thirds cubic units. So not only is Gabriel's horn infinitely long, not only does the surface area, even though it's infinitely long, the surface area exist, the volume exists too. What? What are you talking about? That's crazy talk.
Magic of calculus.
That's magic. Okay, so pi over 3 cubic units, and that's not a lot. Pi is a little bit more than 3, right? So a little bit more than 1, say, cubic foot if x is in feet. Okay. All right, let's go. Any questions up to here? We okay? All right, let's go back to the top. Can you evaluate the arc length? This one. Go ahead. That one's not a U sub or anything, right? So go straight to a convergence table. See what you get.
That goes to infinity too.
You think it goes to infinity? All right, let's find out.
It should. That would be
We'll do the L first. Do L. See what you get for L. All right, so we're doing this table right here. What was it now? It was rad 1 plus 4 over x to the 6. All right, so evaluate that. See what happens.
The first one is 0.
First one is 0? Because 1 to 1, right? Oh, that was hard. Do you need a calculator for that? Nope. Because we're going from 1 to 1. That's it. So 1 to 10. Ronnie, you owe me a test, you know.
Ronnie.
The makeup. The makeup, right?
Yeah, the makeup, right? All right, did anyone get from 1 to 10? What'd you get? What'd you get? Did you get?
Still, I think it doesn't.
You got 9 point something? What?
Converge. So I'm not doing
9.3. 09. 17. Okay, let's run off the 4 places. Who got to 100?
99.09.
Go say again.
99.09.
99.09.
No. 0.309.
Oh, 309. 309. So the same thing? 3092?
Yeah.
Yeah, okay.
It's just.
Yeah, that's weird that happens. 3092. Okay. Well, do you really have to do 1,000? What do you think this is doing? Okay. It's divergent. So the arc length, D and E. Okay. What about the surface area? Let's do it again for the surface area. All right, so let's see. We're going to do this table now. The integral from 1 to b of 2 pi times the radius of rotation times the arc length differential. All right, let's evaluate that. And again, from 1 to 1 is 0. Okay, so that's silly. All right, so 1 to 10. Let's see if this one converges. Doesn't have to, just because last time it did. Sometimes the surface area converges and the volume doesn't, and vice versa. Sometimes the arc length converges and the surface area doesn't, vice versa.
Wait. The surface area would converge, but the volume.
But you have the 2 pi. That's arc length and the surface area. There's a 2 pi 1 over x squared.
This is different than our
Really? So we got something like that. Yeah, round over to 4 places.
Yeah, you're okay. Wait, how would the surface area
It's very weird. That's why it's called improper. It's very weird behaviors going on here. We'll talk about why they converge and why they don't converge when we get to power series.
One that
They all are different. Okay, who got to 10? I mean, yeah, who got to 10? Nobody? What do you got? 9, 838. Okay, did anyone do 100? What? 75492. All right, did you do 1,000? It's not clearly convergent yet. 76057. How about make it 9? All right, how about 10,000?
no,
115, really? Well, this is converging, but very, very slowly. If we stop here, what's your best answer? What has converged? 7.6 matches up. All right, so I'm going to say this is
I
about
got fourth place.
7.6. I don't want to
$10
go on forever with this thing.
I got 10 million.
You got 10 million, really?
Yeah,
To
dude.
convert.
All right, now I want to go back. Any questions how we did that? We have to come back and talk a little bit more about improper integrals. We're not really talking about that yet. We're going to spend a whole day on that sometime soon. Just like L'Hopital, L'Hopital comes up a lot. We haven't really spent a day on that. We're going to come back to that at some point. We're going to do that. But I want to go back to this one back here. There was one back here, I think over here, that I think you don't need a table for this one either. Do you? Let's see. What is e to the negative x really? So if you distribute 1 over e to the x into the radical, how do you do that? You square it, and you get 1 times 1 over e to the 2x plus, so you get 1 over e to the 2x plus 1 over e to the 4x?
Yeah.
That's even worse. Can you integrate that? No. But is that a use of? As it's written, is that a use of? I'm going to say that I have a feeling we don't have to do the table here. Alrighty. Let's see if we can get away without a table. If u is who? 1 plus
1 over
e to the negative 2x, right?
Yes.
So if that's u, what's du? E to the u du. So how do you replace, this is u inside the radical, right? But how do you replace the dx part? I take it back. I lied. Why can't you? Because I have dx and e to the negative x. I have dx and e to the negative 2x. Oh. Yeah, no, we're stuck. Yeah, I was trying to see if we could do it exactly. No, a lot of these you have to do by table. Yeah. They don't come out easy to anti-differentiate. This is not an easy anti-derivative, right?
Unless it was e to the x or something. Because then the derivative will be the same. As because when you square it.
Right. All right, how about this one? This is 91 BC4. It says cap f is this integral expression. Can you get the arc length from 1 to 2 of that curve? If you were to graph this curve, that's a 2x up there. How do you get the arc length? Well, first you need the derivative. So what's cap f prime? Remember, you take this and you plug in 2x, so you get radical 4x squared plus 2x. But if it's not just x, you got to do chain rule. Times 2. Okay. That's the derivative. Why do we need the derivative to get the arc length? Because you got to square it, right? It was 1 plus the derivative squared in a radical, right? So square it. What do you get? 4 times that. Get rid of the radical, right? Technically, that's an absolute value, but in this domain from 1 to 2, I think they want the arc length from 1 to 2. It doesn't really matter. So how do you find the arc length? The arc length will be what? Whoops. The radical 1 plus that thing we just got? Okay. The integral from, they want it from 1 to 2, okay? Alrighty, so there you go. Now, can you do that as a u sub? Or I mean, well, not as a u sub necessarily, but can you do that algebraically? All right, let's make some room here. How would you do that algebraically? Distribute the 4? Okay, so the integral from 1 to 2 of the square root of 1 plus, well, let's see, 16x squared plus 8x. Well, realize that 16 squared plus 8x plus 1, you can factor it. And it's a perfect square trinomial, right? So what are the factors? It's 4x plus 1 squared, right? Can anyone do a tricky try here? All right, so I'm going to say it's the integral from 1 to 2 of 4x plus 1, because 4x plus 1 times 4x plus 1 is in the radical. That's what we have. So what's nice about these problems, sometimes you get a perfect square that you can get rid of the square root. So this is 4x plus 1 squared. The square root gets rid of it. Technically, that's an absolute value. But from 1 to 2, it really doesn't matter. And so it's easy. So what's the power rule say now? 2x squared plus x evaluated from 1 to 2. Plug in 2. Dang it. Yeah, plug in 2, you get, what, 4, 8, 10, right? Minus. Plug in 1, you get 3, so 7. Amazing. That was 91 BC4. How would you have fared on that test? On that question. Is that terrible? You got to remember the fundamental theorem of calculus part 2 that says how to take a derivative of an integral expression like this, right?
This was no calculator, right?
And there was no calculator required, was there? Yeah, 91. Yeah, 93 was the first time they allowed calculators, and it was only scientific. 95 was the first time they had graphing calculators. So 91, you had bearskins and stone knives, just like we did. All right, so is that terrible? That's not terrible. So look for an easy U sub or an easy square. Sometimes these things simplify nicely. Okay? Don't forget your homework tonight. Page 420 multiples of 4 are like these questions we just did today. If you need a homework checkie, and many of you do, there's not a lot of homework checkies left. You better hurry up and get them made up. Whatever I said. Alrighty, and don't forget the makeup exams. People still always do makeup. If you missed MCQ Monday yesterday, you got to make that up too. It's on the portal, yep. It's on the portal.
Mr. Garcia, can I print something?
Yeah.
Alright, how do I do that?
Oh, that's another question. I can't help you. I'm getting ready for next period, so you got to figure it out.
Connor, how do you print something? How do you print something? Control P. Control P. Control P.
No, because okay.
Titles aren't supposed to be underlined in MLA format. Is it really, Danny? Come on, Danny.
I always underline.
Come on, Danny. Get better. Do better. Do better, Danny.
Oh, wait, YouTube is still going. Sorry, YouTube. It's still listening to our random noises. We're leaving class. Bye-bye, YouTube. Have a nice